collaborations and friendships in science is so key. It's like your tendrils, reaching out, and the more people that you do good deeds for and you have good collaborations with, and the more successful you'll be.
I can't think of any more human activity than conducting science experiments.
The game I play is a very interesting one. It's imagination in a tight straitjacket.
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together.
What I always think should be the basis of education is not answers, but questions. We should teach kids how to question.
This is BLab Codes. My name is Amit Siddiqui. Today on the podcast, we have my friend Sandy, who's working on building nanocages. His research is really interesting because it has so many applications. For instance, these nanocages could be used to deliver drugs for therapies. But what Sandy is most concerned about is the environment and climate change. And he's focusing on building nanocages that could potentially trap carbon dioxide, which would mitigate the effects of global warming. Sandy has had a very interesting journey in science, and he's an awesome dude. I really enjoyed my conversation with Sandy. I hope you guys too.
Sandy Craze, Alexander actually. Sandy's short name, Irish and Scottish.
Okay, cool.
Long line of Alexanders, and I'm the last.
So is your dad an Alexander as well?
No, I've got like three cousins. I've got an Alexandra, Al, Alex, and Sandy. So.
Oh, nice. That's cool. Is anyone related to Alexander the Great?
I wish. Oh. Not Macedonian, it's Irish.
It's Irish, unfortunately. And I was just going to say, what do you do at the moment?
So I'm doing research. I'm in my Masters of Research at the moment in metallo-supramolecular chemistry. So we look at really large synthetic chemistry, so using big organic molecules and trying to piece them together with metal ions into forming metal-directed assembly into forming really large functional structures.
Okay, so you're building these large structures by using molecules, but you're coordinating them by using metals.
Exactly, it's like a building. You got you can think of the ligands as like the framework to the building almost, and the metal ions are what come in and hold each end of the frameworks together to piece it into and direct it into a bigger structure.
Right.
And that way you can it's called self-assembly. In other words, kind of like what our body does. It directs the synthesis of these large compounds through metal ions and, in different proteins, right? The active site. Mm. It's a metal ion in a certain environment.
Right. Yeah. That's so interesting. I want to get back to your research a little bit later, but what I'm interested in discussing with you at the beginning is a bit about you when you were younger, as in, right? So everybody goes through a different journey. I was always into science. I didn't clearly know what I wanted to do, but I knew the field of science really interested me. I'm curious about what your disposition was when you were a young child or boy.
Young Sandy. I always knew that science was my passion. I mean, it's from a young age. I just always, I think people got a bit sick of me always asking, but why and how and right. One of the first books Mum ever got me was, I've still got it at home. It's like, what's this made of? Or something like that. It's like a chemistry for like 3-year-olds.
Wow.
And that just always fascinated me. But as a kid, I knew I had this passion for. I always enjoyed it, but I was just so busy, as every kid is, wanting to be the next, Australian cricket captain or the next Harry Kewell. So I was, played a heap of cricket and didn't have too much time at school until a bit later on when I got to year 11 and 12 and.
Did you have aspirations of becoming a professional cricketer?
I did. It only was once I started. When I came out of the HSC and started uni, I was still playing cricket quite competitively. And then when I realised I had that my passion for science was taking over, my passion for cricket, that's ultimately what it came to.
And why did your passion for science take over cricket?
I guess I got to that stage where, in the HSC, you're learning chemistry and biology and physics, but it stops at a level because they're not really asking you to comprehend much, right? It's the HSC is so much regurgitation, so it was still cool, but I wasn't really enjoying it as much as when I got to uni. And they're just teaching you to think, and the science got really cool.
Okay.
And I had a couple of really good lecturers and really good supervisors who just kind of really made me tick over. So.
Right. So you said you were interested in science. I'm assuming in your HSC for year 11 and 12, you did some science units?
Yeah, I did chemistry, physics, and biology.
Oh wow! So you did you're the triple threat, man.
Did the triple threat. It put a bit of a sting on the rest because it meant I had to resort to like my 9th and 10th choices for other things because the lines that would clash, obviously. So I ended up doing like business studies, which was 10th choice.
Right. Okay. So were you good at math in high school?
I guess you have to be for physics and chem.
Right.
I enjoy it a lot more now. In high school, you don't quite see the use of it.
Yeah.
Once you start getting into the real world of chemistry and physics, you see all this how useful this stuff is, and you wish you had paid more attention.
Oh, for sure. When you actually see it, and I think that's one of the things I'm really sad about when it comes to high school mathematics. I think we don't see the application enough. I did 3 in the maths and then dropped to 2 in the maths in high school. But I remember throughout the whole time, I was thinking, this is useless. I'm never going to use maths. When am I even going to use maths?
But don't explain what it could be used for.
Yeah.
That's such a shame.
Dude, it's... and then I was watching a lecture by, I think there's this guy called Richard Arthur who wrote Mathemagics. Solving X to figure out Y or something like that, and it's all about like just the beauty of math, its application and the cool patterns that exist, and it's so it's so. I just thought at that time, like if I had this in high school, if I had passionate teachers, like I would have done maths and possibly gotten into like I don't know.
That's what it comes down to in the end, isn't it? It's passionate teachers. I mean, I was talking to even just here at UWS, Burkhardt. Schruer, he was saying in Germany quite often what they had was the lecturers. So someone who comes out of a PhD is they set the wages not too different as a high school teacher and the graduate job coming out of your PhD. So you got all these people going, okay, well I'll get the holidays, I'll go teach high school. So you got PhD teaching maths, teaching science. So he was saying that his maths teacher for a few years in high school was taking when they were doing differential equations or something. He'd say, "All right, we've learnt this. Let's go do what Einstein did. Let's take his maths and derive that. And that kind of thing." So showing them actually the really cool things that it's used for, not just
for sure. And more recently, and by more recently I mean once I've left high school, I've become more and more interested in physics. Like I've watched a lot of physics documentaries. I'm just fascinated because I'm more fascinated with the philosophical aspect of physics, right? Describing the universe and nature in terms of words, things I can actually understand.
Big physics.
Exactly, yeah. When you're getting to actually having mathematical models that explain a certain law of the universe, that's when I get lost. But I appreciate the fact that math almost appears to be the language of the universe. I don't know if it's something that humans created, but it's similar to how we created language.
It's the way you're describing it, right? It is a language. You're describing the universe.
Exactly.
That's what it is.
And it's so intrinsically involved with how the universe works. I just keep thinking, if I understood that back then, if I understood that by learning maths, we're learning the language of science essentially, right? Because yours is chemistry, but mine's biology, physics. Every field of science has to use maths in one way or another. And it's a shame that we get these high school graduates, including myself, probably not you, but including myself, who had a bad taste left in their mouth because it seemed so esoteric and far removed from real world life.
Yeah, no, I agree, and I think 100% it comes down to how it's taught, and whether someone is passionate enough to pass that passion on. You know what I mean? It's someone speaks to you with a passion about something, it ekes into you. It seeps through, and it's infectious. I mean, I had Roy Tasker in first years.
You had Roy
WS in
Tasker.
chemistry, and that was what really put me down the chemistry track. I thought maybe biochemistry or even biomed or something like that, until I had that year with Roy Tasker, and then it was just never looked back.
I was going to ask you why you got into chemistry rather than other fields. So you had a really phenomenal... Roy Tasker, for the guys who don't know, was nominated as Australia's
he was awarded actually.
Oh, not okay. Yes, sorry.
Lecturer of the Year,
Lecturer of the Year, which is, dude, that's so cool. Do you know what I mean? Like, there are so many lecturers out there, and to be named as the Lecturer of the Year, that's phenomenal. So you had a really great teacher.
Yeah, and his research was into the communication of chemistry.
Oh, really?
Yeah. So he I think for a little while he'd stopped any chemical research, and he was more based on the translation, the teaching of it, and that was just
right. It's a science communication aspect of science.
Yeah,
that's interesting.
So he was really good. He had all these models always on this Odyssey program on the big screen on his computer. They'd always show you, so you weren't just seeing 2D figures on a page. You were seeing things bump into each other and run around the screen, and things gave you more of a 3D understanding of what it is, and that's really important in chemistry. I'm sure it is in biology too, not just to have this 2D, what you see on the page interpretation of things, but to understand that it's moving and dynamic, and what's happening in reality.
And I think that's so much more important for chemistry, because biology, you have, if you're looking at a cell, you can look at it underneath a microscope. You can build 3D models, right? But chemistry, it's so abstract. Because
and physics even more so.
Physics even more so. It gets even more trippy. But these are so abstract, and having models and even analogies can be so useful for students. I know it was for me in high school, because it gives you something to connect to and associate. You're like, oh, okay, it works like this. Like electronegativity, I would always associate to a greedy friend that I had from high school. He'd be like, hey, so because you got lunch, bro? And he would just steal everyone's lunch, just like chlorine steals hoards electrons. And so like those sort of analogies always helped me, and it just shows what a great lecturer he must have been to actually understand that and know, because chemistry is so abstract, it's good to just show 3D models so that students can understand this stuff.
I mean, talking about the maths from before, how he would actually do a lot of his lectures was he'd start at the start with this 3D model example, and especially when we got to the stuff that was a bit more mathsy, a bit more maths based, kinetics and things like that, and he would show you these models and show you the stuff reacting, and build you to the point where you derived the equation for this phenomena without having to even think about numbers. You would just, you know what I mean? You
it was
were
just
looking
logic.
at physically what was happening, and then it's just logic. You know what I mean? Rather than the first thing you see is the equation.
Right.
And then he tries to describe to you what this equation means. It's like you've derived that without even seeing any numbers. It was just the physical things bumping into each other.
Right. And that would prevent, because what I find, and I'm sure you do some teaching, do you do any sort of demonstrating? Yeah. So you'll find with a lot of students is if they perceive something to be difficult, they just shut themselves off, right?
Yeah.
Even though they can learn it, if they just don't come in with a bias, like, oh, it's too hard for me, I can't do this, oh, I'm not even gonna bother. Whereas if you come, like how Roy did it, come from it in an angle where they don't even know that they were going to think it's too difficult, right? You start off with something visual, and then at the end they realize, oh, I can understand this, right? Which just shows how many times we put limitations and barriers in our own learning.
Yeah.
We think something's impossible, and so we make it impossible to learn.
Big time.
Yeah. What I want to also know is, so you're doing a master's of research. You're interested in science and chemistry, but why did you decide to get into research? and not in other fields of science? Let's say you could have gone into medicine, for example. Why research?
I guess it sounds a little bit noble and corny, but I really wanted to make a difference. And that's the I guess in any field you can make a difference. As a doctor, you can make a difference, but my passion has always been the environment, and particularly like emissions. I feel the biggest threat we face, our society, within the next 30 to 100 years, is global warming and climate change. And so, I guess what I'm doing is an area that I can then move into. I want to get in eventually to gas trapping like carbon dioxide and methane and the catalysis and reuse of it. So, thinking how can we take it out of the atmosphere, but then how can we actually turn it into something useful rather than just trying to store it away in the earth or in building materials, or what uses can we make out of it? How can we turn it into in the end something that a business isn't going to do this. These businesses that are producing a lot of pollution, unless you can make it economically viable, can you produce a product they want to sell with their emissions? So I guess that it's a long-winded answer to your question. That's I didn't think about medicine. I thought of that kind of thing because I was just always how could I make the impact that I want to make on society? And I guess it came down to chemistry and physics and trying to look for solutions to end to the problems.
That's really cool. And I'm finding that a lot of people that I have interviewed for this, they want to become scientists. And two things I have to say. But first, they want to become scientists because they have this almost intrinsic desire to make a contribution, to make the world a better place, which is really cool. And I think part of the other reason we were talking about before why I want to start this podcast, part of the other reason is to build this connection between the science community. So if we see students like you, research students, and we see academic supervisors and actually see what the motivations behind their research is, then it's going to be hard to lump all of you guys, or all of us, we should say, in those categories, like as people do, pharmaceutical companies all corrupt, all the science establishment, it's all corrupt. They're all working for the one world government, So
a scientific voice. That's exactly it.
Yeah. So my hope is to expose essentially some of the motivations that scientists have, the motivations that made them get into science in the first place, and it's a cool thing that it appears to be that contribution is the biggest factor. It's the biggest motivating factor for a lot of them.
Yeah, and I mean, if you look at just what you've got to go through to be a researcher, it's you 3-4 years in your undergrad, 2 years in masters, 3 to 4 to 5 years of a PhD. You don't put yourself through 9 to 10 years of university unless you're pretty passionate about what you're doing and you've got a reason for it, and a lot of the time that motivation is a positive,
right?
Into a positive funnel,
Yeah.
Whether it's medicine or the environment or.
Right. I can just imagine some conspiracy theorists saying, "Yeah, that's 9 years, so you can get paid by the pharmaceutical companies. You shill, flat Earth." I don't know.
Come out and working on $70,000 as a postdoc.
Bro. For the guys that don't know, so you have to do 3 years of an undergrad at least, and then you have to do either an honors, which is 1 year of research, or a master's, which is what I've done and what you're doing currently. And then that's 2 years. And then 3 to 4 years of PhD. And after that, you do a postdoc, which is almost like an apprenticeship, right?
Yeah.
You finish your PhD and you're working with a certain lab, but the pay is 9 years of study for.
It's not great. You're learning to become your own researcher. You're getting away from a single group kind of mentality into your own, developing your own research, and the pay's not too great. Yeah. It's in Australia, it's actually quite good,
really,
comparatively. That's why a lot of people think going away for a PhD, where a lot of other countries the PhD students get a bit more, or actually paid a salary, rather than a scholarship, and then come back for postdoc.
Ah, okay. Because the pay is better here in Australia.
Yeah, like relatively, yeah.
Wow.
Yeah, I think it's much higher than America.
I didn't know that.
I have to check that, but
Oh, wow.
from what I've heard, yeah.
Suck on that, America. Some American dude saying, America, yeah.
But they'll all go to France now. You saw that YouTube clip
What happened?
of the new French Prime Minister
No.
asking all the American scientists saying, I know Trump's not funding you guys, so come to France, where we're going to really start funding science and engineering, and we want to solve all these problems, so if you want work, come to France. It's your country too.
Wow, that is so... But I look like this, and by this I mean I look like a Middle Easterner, and I'm sure they've had enough of us going from Syria to France. They're like, no, except you, Hamid. It's like that episode of Simpsons, No Homers. Did you watch that episode? Yeah. He goes into the greenhouse, and there's like no homers, so there's already a homer there. We have enough like Middle Eastern states. So I'm not... Oh man, that's crazy. Okay, so I get it. So you want to get into research because of a sense of contribution. So what are some of the aspirations you have looking into the future? As in, what sort of things you want to accomplish? Where do you see yourself? Where do you want to be? It could be in 5, 10, 20, 30, 50 years.
Yeah, that's an interesting one because, I'm not really so fussed on where I'm doing what I'm doing, or in what kind of establishment. It's academic in a university or industry. I just want to be able to follow what I want to do. Get into the science that I want to be doing, and wherever that is in terms of industry or academia. I'm really flexible and open to that, especially because how quick things are changing at the moment. I mean, governments come in and stop funding something. Like if you're a scientist in America at the moment in academic institutions, you'd be losing funding, while all of a sudden then there's all these rich benefactors like the Gates and Zuckerberg funding startups and all these private industry, and so science kind of moving to the privatization there almost.
Like Elon Musk with his SpaceX. And the Neuralink stuff, it's all private money going to it, yeah. And
and he's all these renewable energy and things. It's so all these really good things that he's doing, but he knows that it's not going to get done quickly with the governments in place. He's taking it into his own hands, and I think that's what's going to happen more. So I'm not really fussed about where I go to do things. I just want to be able to make that difference and do what I want to do. So
sure,
follow that through. But in terms of goals and what I want to work on. I'd love to first finish my PhD, hopefully get a few publications, and then really get into the kind of science I want to work on, because that is unfortunately the slippery slope of academia, right? It's when you're a student, you can only have the project that is available from supervisors. You know what I mean? Unless you got a supervisor who's so lenient that you can come in with him, and he'll say, okay, what do you want to do? Usually there'll be a restriction because of their expertise. And so, then PhD, same thing. You're still dependent on, the expertise of supervisors.
You're still on the tit.
Yeah, exactly.
Yeah.
Then, so hopefully after that, then you can start to, I'd like to branch out and get into what I want to do.
Nice. So you're not too fussed about whether it's academia or industry or policy,
No.
as long as you're doing what you enjoy doing and you're making a difference.
Exactly. And for the students out there who don't know too much about the academic or science in industry versus academia, there's plenty of advantages to both, and there's plenty of restrictions on both. So in terms of career pathway, a lot of people tend towards academia because then you can publish papers and not have to worry about copyright, patents and selling the stuff you're trying to make.
Research,
you can get it out there to the rest of the world and get these papers and try and build up a career based on publishing your work. But then there is this problem with academia in that model where people are publishing stuff, even if it's quite useful, and maybe the 150 to max 500 people, sometimes less than, maybe a community of like 50 scientists worldwide who are in that area might read that paper. and then it's lost. It's lost in the annals of academia. Even if this thing could be genuinely used for something, it could have a use. But in academia, you publish it, and it's unless you can, it's unless you take it anywhere. In terms of application, no one will. It's kind of it gets lost. So then that's the advantage of industry, is you make this stuff and you've got the ability to then take it and make the impact on society, not physically with the thing, not just with the theoretical breakthrough that you're making.
Right.
You know what I'm trying to say?
Yeah, I know exactly what you're trying to say. With industry, if you find something cool, there's funding there to pursue that.
Yeah, to make it into a reality in real life as something that can be used in society.
Exactly. Move from basic science, which is what we're doing, and then applied science is where you take that and you actually try to find some applications, which is, I would assume in industry you'd have more funding and more support to actually pursue the applications. And that's where organizations like CSIRO, which my supervisor worked for, and he can't even talk about, like, I don't know how many years he worked with them, but he can't talk about what his research was about. Everything that he's done is patented, and he's got a non-disclosure agreement so that if he does speak about it, he's going to be in a lot of trouble.
And then so that wouldn't have been published. So now that he's in academia, that's years that he's lost in terms of the academic currency, which is your papers, you know what I mean? So it's that interesting toss-up, and a lot of universities are starting to do some really cool things to get around that, like at Queensland University of Technology, QUT, they've built this new science hub, or this new science building, and I visited it a few months ago when I was up there. They the idea is, I heard the person in charge of the project speaking at a conference I was at. He said the idea is that let's get everyone in the same building. Let's have the chemists on this level, the biologists on that level, the physicists. Let's have them all there, and then let's have the industry contacts and the engineers and the stuff, that when these guys have a problem, the chemists have a problem that they need the physicists for, or they have an application they think they might need the biologists for, and then when this thing's ready, they can take it straight to
engineers
and industry and get it out there and actually stop this almost wastage of ideas. It's like you got all these really smart people working on stuff and publishing papers, but then forgetting, like leaving it. So let's get that whole, from basic science, as you said, to applied science in society. Let's get that in the one building so that it can get out there.
Right.
Which is a great idea, and it's what we don't do enough of. I heard Tom Miller make a really good presentation the other day, where he was saying that a great idea would be to build that into the PhD. Make them submit a business proposal as part of your COC. You know what I mean? To kind of get people thinking about that, and get people thinking about how you can take your research and try and turn that into something that can be of immediate value, as well as a lot of research is so theoretical and basic science, but thinking about how you can take this and
to the next step.
Something.
Sure. And he had a I didn't get a chance to attend because I was teaching at a different campus, but I think his idea is so great. I mean, if you're coming out of a PhD and only specializing in one thing, that's the only thing and you don't have these other skills, which is so imperative, like business skills. So just in case you come up with a great idea, how can I capitalize on this? How can I make this available for everyone? But going back to what you said about the University of Queensland, it's interesting because by getting science, I think is more collaborative than anything else. It's so difficult to make an impact if you're in isolation. If you're in the cave like a monk, some hermit, no one's gonna. You can't come up with great ideas. You have to collaborate with people, consult other people with different expertise, and by putting everyone together, chemists, biologists, physicists, engineers. I mean, that's where the magic I would expect would happen.
Exactly. It's as an example, we sent a paper of mine away just a couple of weeks ago. We had a team doing the hardcore physics from China. I've never met them. We had some teams doing the photophysics from University of Queensland, and then we had people from Sydney Uni. So it was all these people with different disciplines from all over the place coming together for this paper.
Mm-hmm.
And imagine if you had that in the one building.
Oh, that'd be amazing.
It's the kind of thing they're trying to get more of, and then you've got more minds saying, okay, is this applicable in society? Obviously, and a lot of the stuff, that could get published, isn't.
Mm-hmm.
But at least you've got the minds there to kind of to think through it.
Yeah, I think it's also a case of chance favors the prepared mind. If you have all the necessary preparations there, so if you have the chemist, biologist, you have the equipment there, you have the facility there, then you're bound to get more lucky than if everyone's in separate, isolated areas of the world.
Yeah.
And to your example, I mean, just it again shows how collaborative science is, where you guys are doing one type of research, but you're relying on other people's expertise to help you essentially achieve your goal and your research aims.
Yeah, and as you said, that's science. It's so collaborative. You, as you said, you can't do something. You can't achieve much on your own.
That's right.
There's so much that you don't know.
Yeah, for sure.
That
for
someone
sure.
else does.
Yeah. Did you guys do a reading in? You're in first year right now, yes?
Just finishing.
Okay, great.
Yeah.
Did you guys do a reading on Stephen Hawking's?
Yeah.
That was an interesting read, don't you think so? Because
the Millet, was it?
I think so, yeah. Where the perception of Stephen Hawking's as in the public is that he's this lone genius, this brain in the vat, but the actual reality is that this guy is being supported not only by the computers and the technology, which enable him to do what he's doing, but all the research students that are pushing his research forward, people who are actually writing the articles, and then he gets the credit for it.
Yeah, and it's crazy that still happens in terms of I hadn't seen many examples where that still happens. Sometimes, only rarely do I ever see, especially in our field,
right,
a paper that comes out with just two names or one name.
Mm.
You know what I mean? Usually, it's as we were talking about, it's many.
Mm-hmm.
But it was interesting to learn that a lot of the papers that he actually does publish is just Stephen Hawking's.
Wow.
Not the names of the PhD or postgrad students who did the majority of the work. Obviously it's his brainchild,
right.
He's given them, when you read it, it was saying he gave them this exact specific
project,
right? And he's handpicked someone from all these math tests and stuff to be perfect for that.
Mm-hmm.
But it's someone else is doing the work, and and then it's just him on the paper. It's very rarely him and
some else co-author. Yeah. You know what I think? Probably if I had to look at it from his perspective, he's like the human being, and the research students are the Google search. He's like, why would I give Google any credit? Right? I came up with the ideas. They're just doing the manual stuff. But again, it just shows that even him, who individual who we think is like this lone genius, is no genius without the support, the network of competencies, as he puts it, that enable him to do what he's able to do. Without those networks and without your networks, without all these physicists and chemists and so on and so from different parts of the world, you wouldn't have been able to get that paper out.
Exactly. And that actually brings up a really interesting point of academia, especially, is that the better you get and the more you learn about your area and the higher up you go up the ranks, the less science you actually do. You've got your minions, and you're coming up with the ideas, and you've got your tentacles, your arms, your students, but the less science you actually do, the better you get, which is as and I guess that's Stephen Hawking's. Obviously there's restrictions on what he can do, but it's quite interesting.
That's an interesting observation, because I was talking to Alex, who's he's in my research group, but we were talking about, I was asking him, have you seen our supervisor, who's Dr. Mark Jones? Have you ever seen him in the lab? He's like, no, dude. I'm like, what the hell is going on? And then I came, exactly. That's what I realized. I think, as you said, you're going from our stage, which is we're doing like each tiny step to figure out what the overall, idea is and how something's working. Whereas he's looking at it from a more global perspective.
Yeah.
And I think part of the argument of that Stephen Hawking's book was that to be successful in science, you have to be in that crossroads where people are coming and connecting with you, right?
Yeah.
And so you're at the crossroads of these networks of competencies, and in Stephen Hawking's, and I gave a couple other examples, but the people who have the most extensive networks are the ones that are the most successful.
Yeah, it's collaborations and friendships in science is so key. It's like your tendrils, reaching out, and the more people that you do good deeds for and you have good collaborations with, and the more successful you'll be.
Yeah. Kind of sounds like religion.
Yeah.
We spoke about your aspirations when you were a young kid, but or even now, I should say. What are some of the fears that you have looking into the future? And it could be as specific and as broad as you like.
I guess there's the obvious, more of a nervous excitement with academia or with science in general, I guess. Is that with how globalized the job is these days, you've got no idea where you'll end up in the next, even during the PhD, if I even do the PhD here in this country, at some stage of my PhD, I'll probably be spending extended time overseas. Afterwards, most likely, we'll be working overseas. So it's kind of a nervous excitement, where there's no kind of set path of where I'll be living. So that's not so much fear, but I guess one fear, when what I want to go into is trying to handle global warming, is the fear of how far down the track we're getting. It's really scary. It's quite depressing every time you think about it. How far down the slope where we're starting to tip before, and how far do we have to go before the majority of the world wakes up to the fact that there is a serious problem. There's this thing called the tipping point in climate science, which is like in the Siberian permafrost, there's just stupid amounts of methane from decayed biological matter submersed under the ice, and as it starts to warm and melt, if it gets to the stage where we start to melt the permafrost, stupid amounts of methane get released, and it's called a tipping point because methane is, as a greenhouse gas, is 26 times worse than carbon dioxide. It stays in the atmosphere longer and traps heat.
So the message is don't fart, people.
Yeah. Well, cover up your cows. But compared to what's in the permafrost, it takes a lot of cow farts. It's pretty scary.
Yeah.
So the idea is once we tip over that point, there's not real
anything we can do.
Yeah.
We're just screwed.
We need a big methane trap.
Wow. Okay. So I get that. That's a good answer. Because some of the answers that I've gotten from other people are just the insecurity of not knowing what's coming up, which is something that you express as well. But it's good to see that you're thinking about how are we going to solve this issue. The
unfortunate thing is that it is a motivation that for it to happen sooner is going to have to be monetary. There's all this vested interest, whether people like to admit it or not, in oil and coal and clean coal. Probably the biggest paradox, or what they call it.
It's just been washed really thoroughly.
That's how washed all the carbon out of it, But unfortunately, that is the struggle for us as scientists who have a passion in the area. Is like, why can't you guys just see the problem and put aside your monetary benefit for this? I mean, this is the future of the planet. This is your children growing up with being able to go and see a polar bear, or even see them on TV, being able to go to a rainforest, being able to go to the snow. Do you want to have your grandchildren and be telling them about, you know, the pandas that used to live, or, you know, that's...
Or the coral reef that existed.
Yeah, the coral reef that existed.
How it wasn't bleached anymore, or it wasn't bleached at the time, yeah.
How we used to have ice on the poles.
Hey.
The Earth used to actually be orientated this way.
Hey.
But,
people used to live above ground, like Matrix.
out of the Matrix.
Yeah.
But no, and that's the challenge, is making it, at the moment, is making it economically viable for industry. Otherwise, unfortunately, it's just not going to happen until it's almost too late. You know, it's for it to happen now within the time we need it to happen. The job for scientists is to come up with the issue, like the problem, but make it a problem that will also make people money. Unfortunately, that's the bottom line. You know, you have to be able to say to a company, yes, I can trap your carbon. Yes, I can do the right thing and stop these emissions entering the atmosphere. But, you know, why would you just pay for this?
Right.
You know, why would you just pay me to do this?
Yeah.
You wouldn't. You would only do it if you're going to make money.
For sure. And,
so, you know,
and companies are notoriously greedy. I mean, oil companies have hired scientists in the past to convince people that lead in petrol is actually natural and good for you. Like, that took 20 years of science. Like, one specific scientist, and I forget his name, but it was in that Cosmos documentary with Neil deGrasse Tyson. It was really, he's a scientist that was able to date the age of the Earth based on the ratio of lead and uranium. So he's the one that figured out, oh no, there's so much lead right now that's never been here before. And they hired like all these other fake scientists to essentially pump this message through Congress in America. No, lead is natural, lead is good, lead is this, lead is that. And I feel kind of, I just hope that we can get it together, and that our personal interests won't get in the way of human survival.
It's hard to comprehend, isn't it? Like, you imagine being one of those businessmen, like, say, you own a mine or something along the coast of Queensland near the reef, and it's hard to comprehend what's going through their mind when they'll make a decision that they know is going to be detrimental to the world, to the environment, to the Barrier Reef in this instance, by dredging there. They could put their waste underground somewhere, or they can dredge it into the Barrier Reef. It's cheaper to dredge it. It's weird to the oil tycoon who to put yourself in their head and make this decision that is making you money but detrimental to the future of humanity,
the planet, everything. Yeah,
it's just weird to try and put yourself in that.
No, I totally get it. I mean, if you even with that lead example, for instance, with that lead example, those people who were funding these other scientists to talk or tell Congress that lead is natural, their kids were inhaling lead. They lived in areas that had high lead pollution levels. So it's almost like a mental disease, it seems like. It's like the greed takes over so bad that there's no logic and there's no consideration of the consequences. You're like, man, give me that money. Who cares about everything else,
Yeah, it's weird. It's like, if aliens attacked and you had to make a decision where you could save the world from these aliens or have $1 billion, you'd choose to save the world from the aliens because otherwise you wouldn't be there to have your $1 billion. But it's the same thing, but it's just long term. It's weird that people will make.
Yeah, exactly right.
In
I think it's also, as you said, it's long term. It's almost, I think, analogous to how students approach assignments, right? If they have 2 weeks, they're like, I'll just worry about it later, right? And you wake up, like you wait till the very last night. And that's where the sense of urgency comes. It's when you see the foreseeable outcome, you're like, oh my God, if I don't do this assignment right now, I'm going to get a 0. Or if you don't change things right now, the world is going to explode. I don't know. I don't know. There's going to be one big cow fart.
Too much methane.
Yeah, too much methane. And somebody's going to light up a lighter and then boom, that's the whole earth gone for you. I don't know. Can you imagine?
We'd be in the Matrix anyway, so
exactly. Just one more question, and I promise I'll let you go. We didn't talk too much about your project. which is a shame. We kind of discussed your project in terms of coordinating the self-assembly large molecules. But can you just elaborate a little bit about your research? Imagine you're explaining it to a non-academic science.
Yeah, so my research at the moment is kind of the wax on, wax off kind of, Mr. Miyagi learning to be able to do the more complex stuff that I'd need to go on and do eventually in PhD. I will start, the gas trapping and things. So at the moment, I'm working with very similar systems, but for a different immediate application. Very, very similar systems though. So at the moment, we're working on really porous nanomaterials and the discrete porous nanomaterials. So instead of things that polymerize into a larger, into a big framework or a polymer.
Right. And a polymer is just a long chain of something, or
repeated
units.
Connected.
It's like a different Lego pieces, the same Lego pieces, just connecting over and over and making long chains of whatever.
Exactly.
Yeah.
But imagine if then you built those Lego pieces into really big, porous structures, which means a lot of area on the inside, a lot of surface area. If you built them into bigger, discrete ones, units, and then put them together. And now what this does is this increases the surface area on inside of these materials by vast amounts. There's part of what I work on are called molecular cages. As I was saying, that we use these metals to build these organic molecules into these pretty much big hollow balls. And the idea is that when you have this insane amount of surface area, and I'm talking as in 1 gram of this stuff can have, if you could unfold all these little nano balls, almost 1 gram would have enough surface area to cover a football field.
Wow.
Easily. And so, and that's an old stat, there's been bigger ones produced since then. But the cool thing about when you have porosity in nanomaterials is it allows you to do lots of really cool things. And that's like the gas trapping was one. Catalysis. So if you imagine things in solution, whenever things react in a solution, there's billions and billions of solvent molecules per your target molecule, right?
Like solvent molecules like water, for instance.
Exactly. You've got salt dissolved in water. And for these things to react, they've got to travel through all this solvent that they're interacting with and then collide with enough energy to produce the product. But if you can, the chances of them doing that, statistically, when you think about it, actually really low. That's why you've got to leave reactions on for a week or, but if you could use this big cage and the solvent and say just 2 of your reagents come in and can bounce around inside this cage and react, the chances of them colliding and producing this reaction gets increased dramatically. So you get catalysis. You speed up the reactions, or even have sites inside these pores that actually increase the rate of the reaction by, say mimicking biological molecules and things by having these open metal sites and things that can produce fast reactions. You've got drug delivery is another avenue. Housing a molecule and getting it somewhere. There's so many uses. Something that my thesis is focusing heavily on is what's called spin crossover, and it's getting into the physics that we were describing before. So it's where you're taking a metal ion that has no unpaired electrons. And when something has no unpaired electrons, it's not magnetic. We call that diamagnetic. But then,
so normally these metals would have paired electrons.
Depends. It depends on the metal. But the important thing about this property is that this spin crossover is that you take a metal that either has no unpaired electrons, it's not magnetic, and either with temperature, pressure, or light, you can make it transfer to one that does permanently until you reverse that.
Oh wow! So you
go from not magnetic to magnetic.
Dude, that's magical. So you could essentially take a metal that's not magnetic at all and turn it into a magnetic metal.
Yeah, and and you can do it in heaps of different ways. And the applications of this in sensors, and the big one is in data storage, because if you think magnetic and not magnetic.
That's 0 and 1.
0, 1, but then there's ones where they don't just go magnetic to non-magnetic. They go through steps where they might go from, if you have, say, instead of, as I was talking about these discrete molecules, if it has one metal, then it might do that. It might go from just, say, on to off, 1 to 0, magnetic to not magnetic. But if in one discrete molecule you've got 2 or 3 metal centers that all do the same thing, but at slightly different temperatures, then you're not just dealing with ones and zeros, you're dealing with 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, you know.
Right.
So the code that you can encompass becomes, so this is quantum computing and data storage, quantum data storage.
Wow, that's interesting. Just in terms of turning a metal into a magnetic one. So let's just say it's a metal that doesn't have any magnetism. So that's when you have 2 electrons that are paired. And if you take away one of those electrons, then what? So how do you make it magnetic? Is the question I'm asking.
I guess a key thing to understand first is there's a difference between the magnetism that we usually comprehend, which is say we take a magnet and stick it
with iron filings.
Yeah, with iron filings, and they attach. That's magnetism on a bulk scale, which means that the metal ions that have these, as I said, unpaired electrons within the material, their magnetic moments all align perfectly so that when you bring a field near it, it can be attracted. There are some bulk solids like that where the individual metal atoms are magnetic, but because they're all aligned in opposite directions,
they cancel each other out.
So this is different. This is magnetism for a single discrete molecule, right?
Okay.
And that builds up in the solid when it in the crystal lattice. And as in answer to your question, how
did you make them magnetic?
Okay, so for anyone studying chemistry in the HSC, electrons can exist in energy states. They're called orbitals, molecular orbitals, and a cool little law in physics, you can only have 2 electrons in one molecular orbital, and they're paired. Electrons have this property, it's called spin. Pretty much it's kind of just like the orientation of their magnetic moment, right? So if you imagine 2 electrons have this negative electronic moment that's orientated in a specific direction. If you put them in the same energy state, this orbital, with that same orientation of this negative charge, this negative, it's not going to be they're going to be opposing, right?
Right.
And so to fit 2 in an orbital, one is flipped with the orientation the other way around.
Right.
So only 2 can fit in an orbital. So if you imagine, now if you have a metal with uneven number of electrons, that will automatically have a spare electron.
Yeah.
Right? But so we can take metals that have 6, an even number, and we produce organic molecules that coordinate, as you were saying, with them, so bind to the metal centers, and they have just the right energy of interaction to, when you increase the temperature or pressure or light, it allows 2, instead of saying if I've got these 2 that are paired in the one orbital, it allows it to go, which is at that stage the most energy, the lowest energy state.
So stable.
The most stable state.
Yep.
It actually allows, as you increase the temperature, this state where one of those electrons moves up into a higher energy orbital to be the more stable state at that temperature. So you're not taking away electrons or adding electrons, you're just moving the energy state that it's within, and then by doing that, you're changing the magnetic properties of the material.
Okay, let me just see if I understand this correctly. So electrons exist in orbits, and for those who don't have a chemistry background, you can think of an orbit like the sun, and you have electrons like the obviously this is very simplified because we know it's not like this. There's different shapes, s orbitals, but let's be whatever. But we'll just go with a simple analogy. You have the sun and you have these planets orbiting them. So Mercury and Venus are the inner orbits, whereas like Neptune and Pluto would be the outer orbits. So if you're in the outer orbits, you have more energy, and in the inner orbits you have less energy, right? Would that be correct? So as your energy state increases, you jump to a higher orbit, so you jump to an outer orbit.
Yeah.
So, and you're saying that you could have these two electrons existing in the same orbit only if they have opposite spins. So it's almost like being in a conservative country where you can only get together if you're the opposite sex.
Exactly.
As soon as you're showing any sort of affinity, like there's no way homosexuality is going to be tolerated in certain parts of the world. So you can only accept opposites, right? Opposites attract.
Except to make them fit, you wouldn't put them in the same room and just turn them upside down. Which is what they're doing with the electrons.
Yeah. That's so funny. And so as long as those opposite electrons are together, there's no magnetism. But as soon as you kick one out, for whatever reason, increasing the temperature, the energy, that one electron jumps to an outer orbit. So it might jump from the Mercury orbital to the Earth orbital. And over there it's by itself, and that's what causes the magnetism.
And now you've got two by themselves.
Oh.
So, so you got two, you go from none to two.
Right.
And so, the example, the systems we use, we go from none to 5 amperes. So it's quite interesting, and you can play with these different metals. So there's a couple that specifically are better than others because the energy levels of those orbitals are within the region that we need.
That's so interesting. So does that mean that electrons by default are electromagnetic? They have a magnetism to themselves.
Oh yeah, they're a charged particle, right? So any charged particle has its own magnetic moment. Protons the same. They have a magnetic moment because when you think about it, what gives off an electric charge, electric field, a magnetic field, is a point of electric charge that's moving, right? Like when you're in year 12, when you took that magnet through a coil, and you created your own little generator. Right. But the same thing with an electron. They're constantly buzzing around, right? A better way to think of it, rather than the orbits, is just a big smear of electrons just around,
like a cloud.
A cloud, because technically they exist everywhere within their orbit at once. So it's whenever you get a charged particle, it's moving, it's producing a magnetic field. Right. And so they do, and we use that in a lot of chemistry and physics. We actually use that to our advantage. The fact that if you've ever done NMR or anything like that,
right. Yep. I've done a bit. I remember from undergrad where you're looking at the peaks to determine the structure of the molecules.
And so what you're actually looking at there is they're probing the magnetic moment, the spin state of the nucleus, right? But they know of the protons and the neutrons, but they know that signal that they get from that is altered by the magnetic field that the electrons are giving off around each proton or neutron, you know what I mean? So they can distinguish the environment of different atoms by
looking at the magnetic moment of the nucleus of the atom.
And how that's affected by the electrons.
Right. That's interesting. Your analogy of, getting a battery and essentially getting a long piece of wire and wrapping it around a nail and then just, attaching that to a battery, that's just electrons moving from the negative, the anode to the cathode, correct?
Yeah. Well,
and that creates magnetism because you could essentially make that...
A moving charge.
Yeah.
The electrons are moving within the material, and that produces an electric field.
Dude, you've just blown my mind. Now I know why magnetism works. Oh shit. Awesome. This has been a really interesting conversation for me. Screw it. I was going to ask you one question, but it's getting late and I'd prefer to just let you as it is. And I want to thank you for your time, Sandy. This was really good. Thanks, man. I appreciate it.
Thanks, man.
So, what did you think of our guest, Sandy?
What a smart guy, hey? Honestly. He's the type of guy that you get really jealous of. He's a triple threat. Yeah. Sports, music, science.
And good looks. Oh,
Yeah, good looks. Yeah. Charming guy.
He's very smart, dude. I was very intrigued. It's you know what I'm finding with a lot of these guys that we interview for this podcast is a lot of these guys are motivated by a almost an obligation to contribute to make a difference in the world, to make their lives mean something.
Yeah. I thought that as well. Like, it makes me feel a little bit bad because when I think about my own motivations, they're a little bit more selfish. You know, I'm kind of just doing science because I like it. And I know Sandy loves it too, and he kind of reiterated that when he was talking about his youth and things. But I don't have any grand aspirations of saving the world, and I think a lot of people are really well motivated, and I think that's something I need to think a little bit more about as well.
That's interesting you say that. I find that certain people have, you know, this clear idea of, you know, they're going to change the world and I'm going to do it through these set of skills. You know, I'm going to make myself as skilled as I can in this field and make a contribution in this way. And others, you know, they're driven by, this is what makes me feel good. This is what I enjoy doing. And I think, I don't believe one is less than the other. I think you're right.
And I think Sandy as well, like, he didn't say this exactly. He alluded to it, I think, in the start when he was talking about his youth as well, because that's something I can really connect with, always being fascinated with, like, how things worked and stuff like that, and pulling things apart. And I think he mentioned stuff like that. He mentioned that book that, the book that I'm going to have to buy for my kids, I think, actually. What was it called? What Is This Made From? Right. For quite young kids, where it just teaches them words about what things are made from and what parts make up, like, technology and things like that. I think it's a great idea. And
wow.
Yeah,
I think that's a great idea. Honestly, I have 2 nieces and a nephew who are around 5 to about 8, and I should get them something like that. It'd be good.
Yeah, because kids as well, and Sandy mentioned this, kids they're like filled with so much wonder about the world and what goes on. They're always asking questions. I think you kind of lose that a little bit as you grow up. You kind of, life takes hold and you get responsibilities and things, and you get, like, less time to wonder. It's one of the things I like about science, actually. It kind of, like, keeps that wonder still there. You get to still kind of chase it a little bit. Yeah, it was good. But back onto it, his motivation for doing good about the world, I do really admire that. And I think it's got to take a little bit of both, you know. You've got to have that passion for what you're doing, but it's always good to be well motivated and have good motivations behind that passion, and at least put that passion into things that will at least make other people's lives better. So yeah, I thought that was really admirable to hear him say that.
You know, but it's also good, he's a student who is, you know, concerned about our future, the future of this planet. He's not an individual that's getting paid by the oil companies. He's not, you know, this individual that people have this perception of science and scientists as this establishment where everyone's in on it. You know, it's almost like the Freemasons, the one world government.
Like big conspiracy theory, you know.
Yeah. You see actually him, you know, you understand why he is into actually making a difference, why he's interested in climate science and why he's concerned. So bringing that human side is so important, in my opinion, because it shows that, no, we're not all these, you know, bots or these devil worshippers that are out there to screw people over money. No, a lot of us are actually driven because we want to make a difference. Whether be it small or big, it doesn't really matter.
And it's that sense of wonder that we're talking about that manifests itself, I think, in that desire to kind of make a difference and find out about the world that we live in and the environment to make a real change. It was great. I think it was really good hearing him talk about the maths as language as well, when he brought up all that stuff about Roy Tusker. Roy Tusker was is a chemistry lecturer, and if you remember from the interview, I think you guys mentioned this, that he won the Lecturer of the Year prize throughout Australia, so it's a massive effort. Chemistry lecturer at Western Sydney Uni. And I unfortunately never had the chance to be lectured by him. I think he was awarded the Lecturer of the Year the year before I started my undergrad.
And you got too big for you.
Yeah. Well, he took the hard chemistries, and I was a little bit more focusing on the easy chemistries. And then, as you well know, kind of went into the biochemistry stuff. So I missed out on lectures from him. So it was really good to hear someone like Sandy really tell me some stuff that I didn't know about him before. Like the way he teaches and the way he introduces concepts and things like that. I thought it was great.
Yeah, and it just shows what sort of influence your teachers have on you. I'm finding on this journey that many people go through, there's just small little things along the path that push them in one direction or another direction.
Yeah, exactly, because he mentions that, doesn't he? He mentions that he wasn't necessarily chemistry bound, I think, before he met Roy. So
he was the triple threat in terms of doing biology, chemistry, and physics.
Yeah,
but he had aspirations of becoming a professional cricketer. So
or a doctor, I think he mentioned as well.
So I think he can.
So it's interesting how one person can actually change your life trajectory in that way. Yeah, it's great. The other thing. While we're on the topic of Roy, I thought it was really great that Sandy mentioned that how Roy used to get them to derive the equations that they were using for these chemistry problems from first principles. And that really hit home with me because I have a hopeless memory due to certain party activities that I did in my youth. But so I can't remember anything from rote. My brain doesn't work like that. I always build stuff up from the ground. I don't remember formulas. I just kind of remember concepts. Yeah, that's right, and how to work it out. And if you know how to work it out, you actually don't need to remember much at all. Because if you understand the concepts, and I like biology. I think biology is maybe a little bit easier to do this with. I think you hit on this in the interview that it's a little bit more abstract chemistry and physics as well. So biology is a bit more easier to do this with. If you learn the concept, I find you don't have to remember the terms as much. And that really helped me as a student, all the way through my student kind of career.
Yeah, and I think it just shows how great of a lecturer Roy Tasker is, in that he recognizes that, a lot of learning chemistry, because it's so abstract and the perception out there is that it's so difficult, he removes a lot of that misconception by getting rid of the math, by getting rid of everything and just bringing back to basics, just using visual aids, and walking people through just logic. And then they understand, oh, I get it. And then you throw them the maths and they're like, oh, wow.
Yeah, exactly. And then they realize that the maths is actually a description about reality.
Yeah.
Which I thought was really good because the first time that really hit me was in my science undergrad as well, when we did a unit, quantitative thinking it was called. It's one of the basic level maths units. But they got us to do an assignment there where we had to write out an equation for whatever we were doing, but we also had to write the equation in prose, so just in normal words. And it really, that was the first time it really hit me that a mathematical equation is literally just a sentence.
It is.
Yeah, it's not like a language. It is literally a language. And it's a language that we use to describe events that happen in the universe, happens in the real world.
That's right.
So you hear these throwaway lines like maths is the language of the universe. I've said them as well, but when you kind of see it like that, like it really is the language that we use to describe the universe.
Right.
So it's really a special thing, I think, maths.
Yeah, for sure. I realized that I think in my undergrad, but I became to really appreciate it in my master's when I had to work on this project for one of my linguistics units where we had to model the tongue shape. So we're looking at the differences between, the articulatory manipulations that singers utilize when singing compared to just talking. So how you change your vocal tract to make your sound, to make your voice sound beautiful. And we had to put these sensors on the tongue, but then we have to model how the tongue was shaped based on what vowel was being said, and all of that was quadratic equations.
Jeez.
And I'm like, wow, you think in high school this is never going to be useful.
Yeah, then you realize, it's true. Because when you're in high school, I don't think you really have that realization that what you're learning is description of real things in the real world. It has that abstractness that it's hard to relate to, and it's maybe a little bit of a failing of the way that people teach maths, but obviously people like Roy are right onto it. I thought it was really interesting, just while we're still on Roy, I thought it was great, I didn't know this, that he's actually done a lot of work on science communication and communication of chemistry and some study on that. I'd love to have him on the podcast. I think it'd be really good to explore that with him.
Yeah, I had no idea, but clearly he's passionate about, science communication and showing people why chemistry is so fun to learn and why it's so interesting and why we should do it and why it's so important to do. It's work by people like Sandy. It's that type of work could potentially change the world because you need more young minds, more fresh blood.
Yeah, exactly. Young people that are really enthusiastic about science,
passionate about it. It's such a sad thing that we see as educators when students are doing a unit that we find fascinating, but they don't care about it at all. It's the saddest thing. Because you're like, hey man, this is why it's so cool, but then we don't know their experience, we don't know their journey, what type of upbringing they had, what type of teachers they've had. So it's like, what can we do more to help students like that become like students like Sandy?
Yeah, exactly.
Who are passionate about doing what they are doing.
Yeah, it's hard work. I liked what he said as well. Another thing that I learned from that Sandy interview was the French president. I forget his name. We're gonna have to put it in there. It's terrible. New French president.
Yep. That's his name.
Yeah, that's his name. Calling all the scientists over there, and I was just thinking, man, my wife who's loves France and loves Paris, just loves the image of it.
Oh, no.
She would like die for me to go and do a PhD in France.
Oh wow.
Don't think that's gonna happen though. Language barrier could be a little bit of a problem. Yeah.
That's all I have to say. Monsieur. I don't know if that's French. It's like that time when Homer Simpson was pretending to know Italian. He was just "Mamma mia, just making up words, pretending like he knew how to speak Italian. That's what I'm doing right now, unfortunately.
You had that great phrase. I thought it was a brilliant phrase about networking in science. I think he said it's like tendrils are reaching out. And that's how you communicate. I think that were his exact words. Great choice of words, Sandy. I've got here on my notes.
Oh.
I thought it was beautiful because that's kind of what networks are like, and it's a bit of a realization I'm having through this Masters of Research that I'm doing with you at the moment. That science is okay. Everybody kind of knows at face value it's collaborative, but I don't think you really get how it has to be collaborative, and if you don't have these large networks of people working together, it's nothing. Science is kind of nothing in isolation. And I think that was a really good take-home message. And he hit the nail on the head there that these networks, you guys talked about the Hawking reading and stuff like that. We'll probably link that. But these networks really make science possible. And you have to stand on the shoulders of giants. So you have to use the work that's come before you. You have to meet with people from other disciplines to get other ideas about it, and that's how scientific progress really happens. So I thought that was really, really great how he kind of identified that as a really key aspect of being a good scientist.
Well, he's had plenty of exposure. I mean, him and Kyle, who's on his research group, they've had publications, I believe, and their publications have only been possible through collaborations with other people, through physicists or other chemists who have the equipment that these guys don't have over here, and it's through collaboration, that it's literally the networks of competencies. These networks enable them to be competent at doing something that they wouldn't
doing things that they would otherwise not be competent at.
Exactly.
Yeah, exactly. So not everybody has skills on every different technique of analytical chemistry, but when you have these good networks, you can utilize the skills of other people to reach greater outcomes than you would by yourself. So it's not even just makes the science better. I think it's really essential to the science.
Very much so. And that extends beyond the science, I think, even to this podcast over here. I mean, I'm doing the interviews. Alex has made the music. We have Michael, designing the website and doing the logo. So it's, again, collaboration. And if it wasn't for this collaboration, we would not have been able to put this podcast together.
Yeah, I think it's excellent. Really looking forward to getting into some more interviews.
You know what I find really fascinating is Sandy's Sandy's project.
Yeah, I loved it. I think when he went through all its applications, that was really impressive. How something as simple as, and let's use it as layman of terms as we can get, porous kind of materials soaking up stuff.
Like a sponge.
Yeah, something like that, a chemical sponge, something as simple like that can really have applications to a whole range of areas that you don't even think about at first. So I think he mentioned speeding up reactions, and so catalysis. So that was basically the same thing, and trapping gas, which is what he hopes to bring it to for climate change and things
also
like that.
Drug delivery, not with the porous material, but definitely with using these nanocages. It's quite interesting. They have these, for those who don't have a chemistry background, what you can do is have these long chains of carbon, these long chains, and you can get them to come together. And he talked about how they're like a framework. If you use a metal, you can actually get them to stick together. And what you can do from that is build a framework that looks like a cage.
Yeah, and I loved how he talked about changing the states, the electrons, the energy states, by using light or temperature or pressure. So then what you've got is you've got a molecule that can change its magnetic state by these external kind of influences. And when it changes its state, obviously that's how you get it to do these types of things, like give up or release a molecule that it's holding.
I'm not sure if that's the case so much, but I think what he was talking about in terms of changing the magnetic states. So you could make a metal like slightly magnetic, more. I think the application for that is more in terms of quantum computing, because you can store data. You know, you can store.
Yeah, he did. Yeah, I've got that written down. Sensors as well, I think he mentioned too, didn't he? Sensors. So,
what do you mean?
So, if they sense light or temperature changes, then they change their state, so they can be used to identify those changes. Then.
Oh wow.
Yeah. I've got it down here. Sensors. He mentioned.
That's interesting.
And data storage and quantum computing, which is something that just came out of nowhere in the podcast. I thought, whoa,
right.
What amazing kind of application of his work.
Yeah, and just, it's so important for researchers to know why their research is important.
Yeah.
And explain adequately, this is the application, even if it's super basic science. And super basic is, just trying to understand the fundamental aspects of nature. In his case, he's building nanocages. In our case, we're trying to understand the fundamental processes involved inside a cell. Applied science, I think we went through this in the podcast, is when you use that knowledge and then you're trying to
make a product, or a new drug or something like that, a new technology. There's a big difference between basic science and applied science, but I think both are really valuable. It's sometimes a little bit harder to find those applications from the basic science because they're not as obvious.
Right, immediately obvious.
They're not as immediate, exactly.
That's right.
But I think it's really important to fund that and for people to kind of understand
why we need to do
why
that.
we need it. Yeah, exactly.
And basic science has funded how many things? I mean, because of basic science, we have the internet. Because of the basic science, like these computers developed. It's always. Scientists are working in conjunction with engineers. So scientists want to run a certain experiment. Engineers need to build instrumentation to run those experiments.
Yeah, exactly.
And these experiments are fundamental aspects or fundamental things that are happening in the universe.
Yeah,
you wouldn't even be able to say why is this applicable, but
a lot of these
in the future
well,
it is.
You don't even know what they're going to lead to.
That's right.
You can be looking at one thing and you need to develop a piece of technology for it, and that technology can be used for something else. I'm going to be sketchy on the details here, which probably isn't great, but I think it was for the SETI program, but the Southern Hemisphere version of it. It's not called SETI, so the Search for Extraterrestrial Intelligence. So essentially that's looking for ET, right? So scientists are looking for ET. And you think, well, what's the immediate value of that? But the immediate value, might be hard to find because they don't find any ET signal. But to look for ET, they have to develop a way of transmitting radio signals electronically and converting them. So they have to develop a computer chip which is now used in pretty much every router and modem in the world, and we get Wi-Fi from that.
Oh snap!
So you get these amazing technologies coming from the most obscure types of basic research. So it's really important to understand that even if you can't identify what your research will lead to exactly, that there could be technologies that come from it that you don't even know exist yet, or couldn't even imagine existing.
Yeah, that's such a good example. And as you were telling me that story, what came to mind was when the Americans had built, they had some sort of equipment built because they had just signed a treaty with Russia about setting off nuclear bombs and atomic bombs. And what happened was that as soon as they turned on this machine, it was just going crazy. And they thought, wow, what the hell is going on? Are the Russians bombing the world? What's going on? And then they saw, no, there's no bombs. And they still kept getting the signal. And then soon they realized, oh, these are signals coming from supernovas.
Yeah, there you go. Yeah, see?
How cool is that?
Yeah. Yeah, sometimes you never know what your research is going to turn up. So
yeah, I think there's value. This might be a philosophical argument, is there value to knowing something just for the sake of knowledge itself?
Yeah, I don't know. It's a difficult question. I've thought about it a lot. Like, how much is knowledge worth? And the other interesting question, maybe this is something we can just leave and not even answer, but another interesting question is, are there some pieces of knowledge that are just too dangerous to know? Yeah, I don't know. I jump around on that. I don't have a set answer.
Yeah, that reminds me of that guy who got crucified for writing that bell curve book.
Yeah.
Forbidden Knowledge, Same Heritage. Check out our podcast on blabcoats.com. Subscribe on iTunes, Stitcher, or wherever you find your podcast by looking up Blab Coats.